Hello, welcome back to Engineering 201 Electrical Fundamentals, and I wanted to go through the sample test. There's on the website, and if you're still having trouble finding the website, I'll put a link to that website in the description of this video. But if you go to that website and you look under the Engineering 201 page and then under the sub page for sample exams, I wanted to go over sample exam number 1. Now, fair warning on this, I highly recommend you print out the sample exam without the solutions. Give yourself an hour and see how you do on it as a good measure of where you are. If you haven't done that, I highly recommend that you now stop this video, you go do that, and then come back and watch this video if you have questions. So you've been warned on that. I don't want to spoil the surprise for anybody, but if you've tried that and you're having some struggles, or maybe even got the question right, and you're wondering, oh, I hope I just didn't get lucky, and you want to know a little more about it, I'd like to talk about that now. So I'll be going over exam number 1, and I've tried to cut this out. I've taken some of the stuff off of it and just put the heart of the material here. So if we look at questions 1, 2, and 3, we'll just go through these in order. On question number 1, it says if all the boxes contain a 1 k ohm resistor, so this is 1K, 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 and 1K. We'd like to find the equivalent resistance between A and B. Well, hopefully that's fairly easy. I mean, if we look at that, we really have these two are in series, right? So 1K plus 1K is going to be equal to 2K, isn't it? And then we could draw that here if we wanted to. So we'd have, and I think, as I mentioned in the other lectures, I think redrawing this plenty is the key to success. So we'd have something like this, 1K and 1K and 1K, and then this would be 2K. Now, you could take these 2 by 2 if you wanted to and use product over sum, but since we have 3 of them, we might just as well say that the equivalent resistance here of this parallel combination is 1 divided by 1 over 1K, that's this one, plus 1 over 1K, that's that one, plus 1 over 2K, which is that one. Okay, and when you go through that, you get 0.4K. Let me double check the math here. I think that's what the solutions have, but just to check it. Yes. Okay. Now, that is just this parallel piece here, so you would still have to add that 1K to it, or if you wanted another diagram, you'd have something like this. The 1K here are just found 0.4K, and we'd recognize then that the answer is 1.4 K ohms. So we would have answer B there. So equivalent resistance problems, those are good problems. Also, we'll build on that when we get into equivalent inductance, and kind of build on that when we get into equivalent capacitance. Well, question number 2, obviously equivalent inductance and capacitance are not on the exam. I want to be real clear on that. We go to part number 2. If the resistors remain the same as in problem number 1, but R2 is shorted out, so R2 is shorted out. So we put a short in here. So in essence, we've got something that looks like this. R2 is shorted out, and then we have a variety of resistors here. This R4 would still be 1K. This combination here would still be 2K, and this would be 1K, but we have this short. This is shorted out. Okay, that's where R2 is shorted out. So we have current coming up to this point. Any self-respecting current is going to go through this dead short. It's not going to come up here and go through 1K, or worse yet, through 2K. So effectively, that removes that part of the circuit, and we could rewrite the circuit really as that, a short circuit. So our answer would be C, 1 K ohm. Okay, so when we short that out. Well, let's move on to question number 3. And again, I will print these, publish these PDFs on the website also. So Yes, question number 3. So with question number 3, if the resistors remain the same, but R5 is open, so this becomes open. So it would have something that looks like this: a resistance there, a resistance there, a resistance there, and then this, and this would be open. So now no current, current cannot come, there's no path, it's open, so it can't come through there. In fact, there would be no current through this resistor. If this resistor happened to be a light bulb like we talked about in the lecture, it wouldn't be lit, it wouldn't be operating, there'd be no current through there. So it effectively removes this part of the circuit, and we're left then with 1 k ohm here, 1 k ohm there, and 1 k ohm there. So when we do that, I have 1 k in parallel with 1 k, parallel with 1k. That's how I do that shorthand, which is going to be what? Just a half of a k. You could do that as 1 times 1 divided by 1 plus 1, product over sum, or if you wanted to, 1 over 1 over 1 plus 1 over 1. We're going to get you the same answer. So we've got a half k. That's for this combination there, so we could put that then in with series with that 1k. There's 1k, there's the half that we just calculated, so we would have 1.5k. 1.5k. Let's see, I don't see it there. I'll tell you one thing, none of the above is never a good answer. I'm not going to say that I never use none of the above, but oftentimes this is put on the test solely for my protection. If I make a mistake in this problem and I don't have an answer here, and then I try and interrupt you during the test or something like that and say, well, you shall add an answer, it becomes a real mess. But if I make a mistake and I don't have an answer here, then it becomes E. So if I'm guessing, I'm probably just going to look through A through D. Now, I don't think I have to guess. 1.5k would be the same as what? 1500 ohms? There we have 1500 ohms. So looks like that's the correct answer there. Well, let's move on then. I think we had questions 4 and 5. And there's a couple ways that we could do this one. We could say, what was this, 100 volts, and R1 and R2 is 500 ohms. R3 is 1k ohm and 1.5 k ohms. The first thing you should do, dimensional homogeneity. I would not mess around with ohms and k ohms. So let's convert this to 1000 ohms and this to 1500 ohms. And then if we wanted to, we could do some just simple circuit simplification and say that we have this 100 volts here and reduce this all to one resistor. Well, these resistors are all in series, so I'd have 1500 plus 1000 is 2500 plus 500 plus 500 is what? 3500 ohms. So if I wanted this current here, I could say that I is going to be equal to 100, because we're using Ohm's law. V is equal to IR. So I is going to be equal to V divided by R, 100 divided by 3500, which nets me, what am I going to get? 0.0286 amps. Okay, you might want to do that in milliamps, but that would be amps. So then that's the current here, and the current there, and the current there. So we could say then that V naught is really equal to I times, using Ohm's law, the resistance, which we would have 0.0286 amps times the resistance of 1000 ohms, which gives me what? 28.6? 28.6 volts. Do I have that answer? Yeah, looks like I select answer A, 28.6. Now, so you might say, oh, I wouldn't necessarily think of that. Could we do that with something like node or mesh? And absolutely, we could do it with node or mesh. Let me finish up this one, and then I'll start a clean page and do it with mesh analysis. If the resistors and source voltages are the same as problem 4, find the power dissipated in R2. Okay, well, power is equal to V times I, or V squared over R, or I squared times R, right? Let's use that one. I like that one because I got I. So 0.0286 squared times what resistance did we have? It was R2. It would be 500. So when you go through that, you're going to get 0.408 watts, which would be, what, if we said milliwatts, 408 milliwatts. There we are right there. Okay, well, let me go back to this one, because, I mean, we used I here, we used I right there. Maybe you want a different way to calculate I. Let's see if we can do that. So I think the previous way that we did is probably the fastest, but if you didn't see that, that's fine. At 100 volts here, we had 500, 500. This was 1,000. You still have to be careful with your units. And 1,500, all of those are in ohms. And what I'm going to do is I'm going to assume some current going in here. Let me just call that I. And then I could write Kirchhoff's voltage law, or, I mean, if you want to call this mesh analysis, you can, however you want to refer to that. So if we start at this point, we have a gain of 100, so I'll say that's minus 100. I'm going to take gains as negative. So I've gone up through there. Then I'm going to have a drop. I'm going to take drops as positive, so I'm going to have I times 500 plus another I times 500 plus another I times 1,000 plus another I times 1,500 gets me back to my starting point. Kirchhoff says that's equal to 0. So rearranging that, I have what? 1,500, 1,000. I have 3,500 I is equal to, moving the 100 to the other side, 100. I is equal to 100 divided by 3,500. I was more careful with the units. This is in volts, and this is in volts, and each one of these are ohms, so I have volts over ohms, which would give me then amps, which is exactly the same thing we had back over here, 100 over 3,500, 100 over 3,500. So you came up with the same answer for I and could attack the problem then very similarly from there. So as you go through these, don't be satisfied with just getting the correct answer. See if you can get it a variety of different ways. Well, that's 4 and 5. What do we have here? Let's see, page 5. 6 and 7. Using the following circuit, we'd like to, if Vs is 100, find current I3. So we're looking for that one. And eventually we will, whenever we have a couple problems, I always make sure that I do it in such a way that I can get the answers the fastest. So we'd like to find the power dissipated in R5. Okay. Now there's only one source in this, so it tends to lead us to one of the easier methods, circuit simplification. Let's see if we can do that. So let me try that. If this was R1, R2, R3, R4, and R5 is 1K ohm, so I have 1K, 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 and 1K. What is my arrangement here with these resistors? I essentially have 1K in parallel with 1K. and then it's in series with this, so I'll add 1k to that. So 1k in parallel with 1k, whether you use product over sum or the inverse of the sum of the inverses, you get a half. So this is going to be what? 1.5 k ohms, which we could say is 1500 ohms. Okay. So maybe I'll redraw this circuit now. What was my voltage? 100 volts. So I said this was 1500. This is still 1k, so let me call it 1000 if I'm going to use 1500 there. And this is 1k. Again, I will call that 1000. So it looks like if I were to come up with the total resistance here, what would I have? If I were to reduce this to a circuit that looked like this, with one resistor, I'm going to have, what's that going to be? Those two are in parallel, so I'm going to say 1000 plus, because the parallel combination is in series with that. And then I'll have to say, what? How do I handle those in parallel? Product over sum. 1500 times 1000 divided by 1500 plus 1000. So that turns out to be equal to what? 1600 ohms. Let me double check that. I think that's correct. Yeah. Okay. So we got 1600 ohms. So now I could talk about this current here. Maybe I'll label that I1 because it's the same as that current right there. I could say that I1 is equal to, what's that going to be equal to? Ohm's law, the voltage, 100 volts divided by 1600 ohms. And we have 0.0625 amps. Okay. So that's I1, which would be the same as this current here. So I could, that's I1 also, isn't it? So if I split this, there's I3, right? So what would I3 be? You could say over here is that therefore I3 would be equal to I1, 0.0625 amps, the total current going into this point, divided by this resistance, which is 1500 ohms, divided by the total. What's the total of these two? 2500 ohms, right? Which gives you 0.0375 amps, which would be what? 37.5 milliamps? 37.5 milliamps. Okay, so it looks like we got answer B there. Well, if the resistors remain the same, find the power dissipated in R5. Well, what we could do is we could figure out I2 and then split I2 again if we wanted to. So I2 is going to be equal to 0.0625 amps times now this 1000 ohms divided by the 2500 ohms, which gives me 0.025 amps. So that's the current right there, and then that splits again, doesn't it? Now, if this resistance is the same as that, it's an even split. So the I through R5 would be equal to just a half. It's going to be an even split of 0.025 amps. I mean, if you go through strict current division, you take and you multiply by this and divide by the sum of the two, so it's essentially multiplying by 1/2. So you're going to come up with 0.025 0.0125 amps. Then we'll use our old friend with this one and use I squared R. So we have 0.0125 squared times what was our resistance? 1,000, which gives us 0.156, and that's watts. 0.156 watts. What can I do with 0.156 watts? Sure, certainly not 156. Nowhere near 12. 156 milliwatts. We got the milli in there, so I think we're good with that. So that'd be answer A. Okay, and usually I don't, for instance, this problem here, this is about as close as I get to playing a round-off game between, let's say, 37.5 and 35. I'm not going to say if the answer is 37.5. You usually won't find me putting 37.4 and 37.6 on there. So don't select E if you have something that's within reasonable rounding of an answer like that. Usually you'll see me with pluses and minuses and big differences like that. Okay, well, the question sometimes comes up, can you do this differently? And certainly, let's see, if we come up with the voltage here, let's say that I've got, see how I want to do this. Let's say I take this. So I'm going to put this onto the next page. So we'll go through this. We're going to assume that we've gone through this process and we've come up with I3, and we'll say that I3 was that 0.0375 amps. Okay. So what could we do with that? Well, with that we could figure out this voltage here, couldn't we? So the voltage is going to be equal to, essentially that would be voltage 2,3, wouldn't it? And the voltage at 2 with respect to 3 is going to be equal to I3 times R3, which is 0.0375 times, what do we have, 1K on that? Yep, 1K. So that'd be 1,000 is 37.5, right? Okay, so we got 37.5. Now that's the also the voltage across here, isn't it? Because voltage across things in parallel is the same. So I have 37.5 volts across there. So I could figure if I wanted to. I mean, these two resistors essentially combine to what? We said that was one 500 ohm resistor, didn't we? 1K in parallel with 1K gives me 500 ohms. So I essentially have a situation where I have 1,000 and I have this 500 with 37.5 volts across there. Could I figure out the voltage here? Absolutely. Be 37.5 times 500 divided by 1,500. Voltage division. So while over here we used a lot of current division, here we're using voltage division. So when you go through that, 37.5, you get 12.5 volts. So I now know the voltage across each one of these resistors because voltage across things in parallel is the same. So I know that's 12.5 volts. Okay. So let's see. We could use our old buddy power is equal to, we got I squared R. How about V squared over R? So I take 12.5, I square that, and I divide by the resistance. The resistance of this one alone was what? 1K, 1,000, which gives me 0.1563 watts, which is 156 milliwatts. right there. Answer A again. Good. We're good to go. So lots of ways to do these problems. And as you practice this exam, as you go through your homework, don't be satisfied with just getting the answer. Concentrate on looking at other ways of doing it and helping your friends that are struggling with it, and being able to say, well, you can do this, but you can't do that, and the reason why is such. So make sure that you're really going through those pieces and really truly understanding this. Okay, so we move on to 8, 9, and 10. What are they wanting in 8, 9, and 10? If R1, R2, R3 is 1K, 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 R4 is 2K, 2000 is 2K, right? And this is 100 volts. And I would encourage you, write on your test. It'll be multiple choice. It'll be a Scantron, but you'll be able to write right on your test. So I would do this. I'd write on your test. The reason I do this is to make it easy to change different versions of the test. So I can change the numbers very easily and have 2, 3, 4 different problems in the same class taking the test at the same time. But you definitely will want to write this on your test and then go about solving it. Okay, so you'll be able to write on your test, and I would really encourage that. Okay, so we would like to find, we'd like to find V1, V2, and the power dissipated in R3. Well, it looks like, we've got a ground symbol here. We've got V1 and V2. It's begging us to do node analysis, isn't it? Well, I will back up and try mesh analysis on the problem eventually, but let's go through node analysis. With node analysis, I'm going to come up with a couple of equations. I'm just going to arbitrarily put some currents on here. I'm going to say this is I1. I'm going to say that this is I2. I've got that that's IX, so I'll say that this is I3. So if I write the node equation up here, at this point here, at the first node there, I can say that I have I1 plus I2 plus IX is equal to 0. Is that right? I1 leaving, I2 leaving, IX is leaving. Yeah. And maybe I can fit this over here. What about here? I have IX going in, 2IX going in, and I3 leaving. So I will have IX plus 2IX is equal to I3. Is that right? Let's see. IX going in, 2IX also going in, and that's creating I3. Yeah, so we could say that this is IX plus 2IX is 3IX is equal to I3. We're going to make some substitutions for I1. I1, I need to find the voltage potential like that, which is minus 100 plus V1. V1 minus 100 divided then by 1K plus I2, which is V1 over 1K. Is that right? Yep, that's V1 over 1K. Plus IX. What's IX? Well, the current's going to your right, so I have to find this. So it's V1 minus V2. Head V1 minus tail V2. So V1 minus V2 divided by 1K is equal to 0. Make this line a little heavier between here. So if I multiply everything by 1K, I come up with what? V1 minus 100 plus V1 plus V1 minus V2 is equal to 0. So I have V1, how many of those? 1, 2, 3, 3 of those. V1 minus V2 is equal to 100, right? 100 goes over there. Yes. Okay. That's an equation. That's a nice equation. The only problem is two unknowns, so I have to work on this. Well, what did we get for Vx? This was Vx, wasn't it? So I could say that I have 3 times V1 minus V2 over 1K is equal to I3, right? So I've got then did I do this? I need to define I3, don't I? I don't want I3 floating around, so we'll do that. 3 times over 1K times V1 minus V2 is equal to, what's I3? That's that voltage there, which is V2, divided by, this time, 2K. So if I multiply everything by 2K, what do I come up with? I get 6V1 minus 6V2 is equal to V2. We're moving that to the other side. I get 6V1 is equal to 7V2. And that's every bit as nice of equation as this one right here, except it has 2 unknowns. But I should be able to solve those simultaneously, right? So when I solve those simultaneously, let's say this is equation 1, this is equation 2. So solve 1 and 2. And what do you get? Well, I might multiply that by 2, so I get 6V1 minus 2V2 is equal to 200. And maybe let's see, I'll say that I have 6V1. Do I know what 6V1 is? Yeah. 6V1 is 7V2. So I've got 7V2 minus, so making a substitution right there. So 7V2 minus 2V2 is equal to 200. So we've got 5V2 is equal to 200. So V2 is equal to 40 volts. Now I knew I was looking for V1 and V2. I could have substituted differently. Had I substituted in for V2, I would have got V1. But hopefully I get 40 volts down here. Great. Okay, we're on a roll. Now what could I do with that? Well, I could just pop that back into there. So I've got that 6V1 is equal to 7V2, which is 40. So V1 is equal to 7/6 of 40. I think if you run that through the calculator, 46.7 volts. Do I have that answer? 46.7 volts. It's positive. Answer A. Good. So now using the same information as question 8, find the power dissipated in R3. R3. So I'm looking for the power in there. A good way to get power is I squared R, right? What's I? That's Ix. So I'd say this is Ix squared times 1K. Do we have Ix? Well, Ix is this thing right here, isn't it? So grab me a little space over here. I could say that Ix is equal to V1 minus V2 divided by 1K, which is, what's V1? 46.7 minus V2, which is 40, divided by 2. Okay. So you'll take that quantity, you'll square that, you'll multiply it by 1K. I'm running out of room here, so I'll just jump to that. So this is going to then go into there. Make sure that you square it, and you come up with 0.0, because this is 1,000, 0.0449 watts, which is what, 44.9 milliwatts, and we'd better take that as not watts, there we go, 45 milliwatts. I mean, this would be 44.9 milliwatts. I think we better take this answer here, D. Okay? So I think the problem was really begging for us to do node analysis, but if you want to try mesh analysis, let's do that. Didn't leave myself much room for a page number. So put this over here. This is page 7. Okay. So, not real neat work, but on the test again, you're gonna write on the test, and you're graded on your answer here. So if your work gets a little sloppy, that's not a problem. So I guess I've illustrated that aptly to you. So page 7. Then I think we'll do this one more time here. We'll do it with mesh analysis. So let's say this is what, 100, 1K, 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 2K. Now I'm going to put these currents in here. I'm going to go ahead and call this I1. This already has a name, IX. And in fact, this kind of has a name, but I'll go ahead and call this I3. So we can say right off the bat here that I3 is equal to minus 2IX, isn't it? I mean, I3 is just the opposite of that, so it's minus 2IX. Then what are we going to do? Well, I could do a Kirchhoff's law starting here. What's that going to look like? Well, I have a gain of 100, so I'll take minus 100 plus 1K times I1 plus 1K times I1 minus IX. Gets me back to my starting point, gets me back to here, which is the same. So that is 0. So that turns into what? 2K. 2K I1 minus 1K IX is equal to 100. So there's an equation. There's an equation. And if I use Kirchhoff's law for this one, as I go around this thing, I would have what? I could, maybe I'll start here and have 1K times IX plus 2K times IX minus this I3 plus 1K. Now I've gone around here and coming up there, 1K times IX minus I1, because I1's opposing it. Gets me back to my starting point. Kirchhoff says that's equal to 0. So what do I have here then in terms of I1? Do I have any I1s in there? Yeah, minus 1K I1 plus, how many IXs do we have? 1, 3, 4. Minus 2K I3, that's how many I3s I have, is equal to 0. So again, another equation. Let me double check these. 2K I1 minus 1K IX. Yes. Okay, so what you're probably going to want to do is substitute this then into here and solve for I1 and IX. Solve for I1 and IX. I1 turns out with this to be 0.0533 amps, and IX then turns out to be equal to 0.0067 amps. Did I get that right? Yeah. Okay, so I didn't go through all of this. Like I said, I'd substitute that into there. Usually, and one disadvantage in my mind, students usually like writing these equations better. They usually end up with more equations, though, but with modern calculators and whatnot, you can throw those in your calculator and solve it. Although if you substitute that into there, it's not too bad. But those are the answers that you should come up with. Now, what are we looking for? well, we're looking for V1, so we have to recognize V1 is this voltage here, so we could really say that V1 would be equal to 100 minus 1K times I1. Is that right? This current is going I1 through there, so yeah, we'd have to subtract off that voltage. Or if you wanted to, you could say that V1 is equal to what? 1K times I1 minus IX. Either one of those should get you the correct answer. We try this. Yeah, you get 46.6 volts using this as 1,000. That's 1K. So 46.6, we get answer A. Good. So you could do it this way, starting here at the ground state, gain the 100, then you're going to drop, because there's drop across that resistor, or you could just start right here and go right up through that one. Either one of those are going to work for you. Now what about V2? Well, you could say that it was V1. That gets you there. Minus 1K times IX. Will that work? Yeah. Or if you wanted to, you could say that V2 was equal to, you could just go straight up this way, which is going to be 2K times what? IX minus I3. That's that term right here. So when you go through that, let me double check that. IX minus I3. Oh, I have to get I3 for that, don't I? Well, I could probably do that. I3 is minus 2IX. I reckon. So this one's probably the easier one. That's how I did it in my notes. But let me double check this. What would be I3 would be minus 2IX. So I have minus 2 times 0.0067. So minus 0.0134 amps. So I've got 2,000 then times 2,000 times IX, which is 0.0067, minus, well, minus and minus is going to be a positive, 0.0134. Yeah, you get 40 volts there. About 40.2, but the obvious answer there is 40 volts. Right there. So we got answer A, we've got answer C, 40 volts. Okay, and could we come back and do this one? Oh, certainly. Actually, this one is a little easier, isn't it? Because I could really say that this is IX is the only current through there, so that's just going to be IX squared times 1K with I squared R, right? So 0.0067, square it, multiply it by 1K, and you will come up with 45 milliwatts. So I think probably using the node analysis was a little simpler. Certainly if I was stranded without a calculator, this is going to be a lot easier. If you got something that'll solve multiple equations, then there's nothing wrong with pursuing mesh. And again, as you review for the examination, being able to do it both ways is important. Well, that gets us to answer 10. Hopefully that has helped you. I would again encourage you to sit down with a blank test and see if you can reproduce this on your own. When we get together next time, we'll be talking about source transformations and superposition, and that'll lead us into Thevenin's and Norton's theorem. So take care till then, and thank you for watching.